Chemistry of beer. These little handouts. Various compounds in beer. I think beer has over 800 different compounds, depending on which brew you got there, right? Myrcene. Alkene. It's actually got 3 enes, so it's called a triene. It's alkenes. Question we can ask right now, if you watch the nomenclature video, which one of those alkenes is stereogenic? That is, which one can have cis and trans isomers? Not all alkenes can. Need to know such. Lots of alkenes up here. And then over there we have a couple of esters, which often have some sort of fruity type smell. Okay, lots of applications. Intro to alkenes was green, that's your nomenclature, various other things. Were there any questions about the green handout? For example, on the back with the article about refrigerants, here are 3 like freons type refrigerants, okay? But they're named. Don't look at that. Name it and then check your name. Make sure you got it right. Make sure they got it right. They put a trans in front of this one. They put a trans in front of that one. Why did they put anything in front of that one? Because it ain't stereogenic. It doesn't need it. There's no possibility of cis trans. Got to know that type of thing. Are mistakes made? Yes, look down here. This reaction is covered in organic 2, right here. Aldol reaction, organic 2. 4 different products. Problem is, that ain't one of them. It's either a typo or something. So, sometimes I make comments about chemistry you'll see in organic 2. Chemistry of beer. Okay, quiz. Thermodynamics. Any questions thus far on this handout? We have these answers yet. Bond strengths there. Let's keep going. We looked at delta S. Delta S you can assess qualitatively. Okay? Need to be able to do that. We did 2 common examples here. One way is favored, the other way, which is this is the reverse of that reaction. And then we looked at a sort of a miscellaneous example there where it was involved a ring formation. Let's look at delta H. Delta H is easier to quantify with calculator. Here's your one chance to use your calculator in organic chemistry. Everybody got one? Okay. You can add, you may not need one, but I know you like to use it. Give delta H for this reaction. Alkene, reacting with HBr to give this addition product. We'll be covering such reaction in lots of detail. Okay? It's very similar to reaction A, except this doesn't have the methyl group on it. Delta H can be calculated using bond strengths, which are in like a table on the first page. Those will be supplied to you. We look at bonds broken, strength of the bonds broken, and then we look at strength of the bonds formed, and we add it up. What's broken in this reaction? The carbon-carbon double bond, or the pi bond, because the sigma bond remains, right? Carbon-carbon pi bond is worth 63 kcal per mole. Where does that come from? Let's see table 1 on the front. I'm going to get another handout. Is it on the front? Okay, got to be careful about this. What's shown on the front for a carbon-carbon pi bond? What is it? What's the value? 174. Well, what gives? I say 63. That's because on the front here, the 174 is for the entire bonding, the pi and the sigma. You wouldn't know that unless I told you. Where my number is just for the pi bond. It came from a different table. Okay? That's why it's different. You got to be careful about such. I just know that that's the entire bonding there between the two parties. Okay? What else is broken over here? Anything else broken in this molecule? No, the CH bonds are still there. The HBr bond is broken. We have HBr. It's now gone. There's no HBr. HBr is, what does it say in this front table? 87? Yes, 87. These add up to 150 kcal per mole. What's formed? We got a new CH bond. There we got 4 CH bonds. Now you got 5 CH bonds. There's one new. And we want to designate what type of carbon is the CH bond. It's primary. Where's the new H bond? It's here. That's a primary carbon. Primary CH. What's it say on the front table? Where's the value on the table? No, not 105. That's H2O. A methyl carbon. A methyl carbon is not a primary carbon. What's the definition of a primary carbon? It's a carbon that's bonded to. Yeah, methyl is not bonded to one carbon. So methyl is not anything. It's not primary. Primary is the next one, 101. They actually have 2 different primaries shown. I don't know why, but they're both 101. All right, and then a CBr bond. Now I don't clarify here the carbon. Sometimes tables give different carbon types. In this table, this bromine is bonded to a primary carbon. In the table, it would be what? 72. 72. Yes, I got 69. That's because I was using a different table. Okay? Whenever I did calculations, my table had like 63. Sometimes tables vary a little bit. Don't let that confuse you. Okay? We broke 150. We formed 170. What is delta H? Okay, negative 120, how do you know it's negative? Why is it not positive 20? Is this reaction exothermic or endothermic? Exo. How do you know it's exo? What? You're going in a circle for me though, but how do you know it's negative delta H? Because it's exothermic.
It produces more energy.
Produces more energy, then it should be. It produces more energy. What do you mean it produces
It
more energy?
releases energy.
Or it releases from the new bonds.
The new bonds have more energy? Does everybody agree the new bonds have more energy? No. The new bonds do not have more energy. The new bonds have less energy. How do you know it's negative 20? How do you know it's exothermic? Why?
Isn't it when you form more stable bonds?
That's what I'm afraid of. You use a formula, but you can't explain how the answer really.
Isn't it when you go from a less stable to a more stable, it gives off more heat?
Uh-huh. Yeah.
And which is where
Which side is more stable?
the right side.
Why is the right side more stable? Higher number. Because these are bond strings, stronger bonds. Stronger bonds are more stable, right? If they're more stable, that equates to them being higher energy or lower energy? Lower energy. These bonds are lower in energy. You got a certain amount of energy. Now the bonds are lower in the energy. Well, where did the difference go? You can't just energy can't just disappear. Where did the energy go? These bonds no longer contain as much energy.
It was released.
They're released. Yes. You get this plus this. You get this plus 20 kcal per mole. You release that. You release 20. Since you released it, what's delta H? Negative 20 kcal per mole, right? Because you released it. These bonds are more stable, thus they contain less energy. How much less energy? The difference. They contain 20 kcal per mole less energy. And that was released. It's a bond strength, not a bond energy. We made stronger bonds. Everybody agree we made stronger bonds than what we had over there? Stronger bonds are lowered energy. Thus energy had to be released to go to that lowered energy. Yes, the equation says you subtract one from the other area. 150 minus 170 is negative 20. But do you really understand what's going on here? Why is it negative? Why is it exothermic? Yes, this is an exothermic reaction right there. We calculated it using bond strengths. Yeah? On the back you can see this reaction is favored by enthalpy. Exothermic reactions are favorable. What about the T delta S term? Because remember, delta G has two terms. It's this term and then this term. This term is favorable for this reaction. It's exothermic. What about this term? Is that favorable for this reaction? Is delta S favorable? We did examples up there. How about here? Is delta S favorable? No, why not?
It lost this.
Two molecules reacting to make one. That's gaining order. That's not gaining disorder. Favorable by delta H, not favorable by delta S. So what about delta G overall? Hard to know because we don't know which one is greater magnitude because we're not doing any calculation for delta S. Let me ask you a question. Would you want to, if you wanted this reaction to go maybe faster, faster reaction, easier reaction, would you heat this reaction? Would heating this make this react faster and give you a better outcome? How do you know? No.
Because it doesn't require additional energy for the reaction to happen.
Why not?
Because it already gives off energy as it is itself.
No.
Or endothelial.
Diamond reacts with oxygen, very exothermic, gives off lots of energy. Do the calculation, very exothermic.
It's spontaneous.
But does a diamond react with oxygen? I mean, we got diamonds all over the place. They don't react with oxygen, even though it's very exothermic, because you got to think about kinetics and stuff. Just because it's exothermic doesn't mean it's going to happen. To get diamond to react with oxygen, you probably have to heat it very high. Then it may start reacting, like with a torch. Do you need to heat this reaction? Will heating this reaction help?
It would make the T delta S term greater.
Okay, we need to look at what temperature is involved. Temperature. Temperature magnifies which term? Delta S. Is delta S favorable for this reaction? No. So why would you want to magnify that? You don't want to magnify a non-favorable component of your reaction. Heating it is going to make it less favorable because your temperature magnifies, right? You know that, right? You talk about such in chem when the heat reactions, T, temperature. Actually, we're not going to heat that reaction. Heating it, turning the heat on high, you're not going to have to. Maybe you need to heat it a little bit to get it over some activation energy, but little as possible. More heat is going to actually make it slow down and not react, okay? You got to know your terms. Calculate delta H for this reaction. Could you do it? What do we need to do first?
Figure out what bonds are being broken. and what
Bonds
can't be.
broken, bonds formed, yeah? Okay? You can do that on your own. Some questions here. Repeat the reaction using iodine instead of F2. Just replace that with iodine and do the calculations again, and then answer some questions. Question?
Is there a reason you prefer kilograms instead of like kilograms?
Just, that's what I grew up with.
Did you do more kilojoules per mole in Gen Chem?
Yeah, it's just,
Yeah.
Okay, I don't know why.
Kinetics. What was the first half of this? Now kinetics. Kinetics describes the rate of reaction. Okay? Mainly depends on activation energy required for the reaction, just like in the diamond example. Here we're going to have reaction coordinate diagrams. Sort of a graph or a plot of the progress of the reaction here on the x-axis and some type of energy listed here. In this reaction coordinate diagram, we have reactants with some type of energy. Products shown here. Okay? Very often we just sort of have a line here and a line here. This would be the delta G. Now, we might just call this delta H, particularly if we just do a bond strength calculation, that would be a delta H. But in general, you can also just show a delta G, but again, depends on, can we calculate all this for us? So these types of things can vary. Again, for us, it'll probably be just delta H, because that's what we can more readily calculate in here. So this reaction would be exothermic. The products are have lower in energy, most likely because they have stronger bonds. But this was the energy of the reaction. We didn't just magically go from here to here, we had some pathway. And the pathway actually required an input of energy to get over some type of mountain. This would be called what? This peak energy here.
Activation energy.
Now the activation energy. And what we know what the reactants look like, we know what the products look like. What is this here though?
An intermediate.
Not an intermediate. An intermediate would have a discrete energy well. Intermediate is not shown. Here's an intermediate. It's got this well where the energy falls into this well. Not an intermediate. What is this at the top here? What do the compounds look like there? Transition state. Okay? This is where they're reacting. Okay? Here are the two reactants. Do they just boom, magically react and form something new? Or do they do something like this? You got to react too. Wait a minute, I had to raise my arm. Or move my molecule or something. That takes energy. All right? There's a transition state. Things are going on. And then we fall down to these bonds made. It's exergonic, we're using delta G. If you're using delta H, we call it exothermic. The other reaction would be a endothermic reaction. Okay? So these are reaction coordinate diagrams. Let's see what type of questions. Which reaction is most favorable of these four? Exothermic, exothermic, endothermic, endothermic. It ain't these two. It looks like they're pretty similar, but actually, isn't B more exothermic?
Yeah.
I mean, it's not that big of a difference, but that is a little bit more exothermic than that. It looks like B is most exothermic, which would be most favorable. B, yeah? Which favorable reaction is fastest? Well, the top two are favorable. Which would be fastest? This one's most exothermic.
Takes more energy to get it started.
Which one's faster? Yeah, that one's faster. But it ain't most exothermic. Because when we talk about fast, that's a rate, and rate depends on what? Activation energy, transition state energy. This one's going to be faster. At a given temperature, this one's going to be making it over the hump more often than this. What's involved here? You're talking, I know in Gen Chem we talk about collisions, okay? These have to come together just right. Sorry, we're not coming together right. Boom. And that's actually the highest energy. I'm not coming together right. I'm not coming together right. Oh, here, you know. This one is easier to come together. It's just lower. So A would be fastest. That's a rate question. Kinetics. Activation energy. Lowest activation energy. That's why it's faster. And that's the problem with diamond reacting with oxygen. Very exothermic. The problem is the activation energy is so high as well. On the other hand, there are other things that react very exothermically, like TNT. All right, it's dynamite. These things also they react very exothermically to give other products. These things typically have low activation energies. It's too low, it's dangerous because it'll just detonate upon transport. But usually explosives don't take much. Usually they're trying to get them to have higher activation energy so they're safe and you can make them only go off whenever you want. But there's some you can just sort of tap, contact explosive, and that's enough energy to make it do its thing, get it over the hump, and then all the energy comes out. Okay, the one at the bottom. Yes, there's an intermediate down there. This is a two-step reaction. We have a transition state leading to an intermediate. Okay? And some energy well. See here, this is where the bonds are forming. The process of forming those bonds to make this actual structure. It's an intermediate structure, often charged. This was where the bonds are being made. That's a higher energy. Okay? Transition state, sometimes also called what? Activated complex. Ever heard that term? Okay. Energy well for the intermediate. Then the intermediate does another reaction with a transition state, leading to a final product. Down here, which is the rate determining step? You've got two steps. Forming the intermediate and then the intermediate forming product. Which is the rate determining step? Yes, the one with the highest activation energy. And usually that makes sense. Forming the intermediate, which is usually charged, forming a charged intermediate is usually going to be your highest energy step. From here, we're falling downhill to this neutral product. Usually it doesn't take much activation energy to fall downhill. So usually such a step is going to be a small activation energy. It takes more energy to go uphill. It's like stairs. It takes energy to walk up the stairs. Fall down the stairs, doesn't take much energy. Go to the top of the stairs, just do this. You're going to go to the bottom. Doesn't take much energy. It's very common. Let's look at some others over here. Sort of just what I said is two different intermediates. Usually the lower energy intermediate will have the lower transition state energy. Very common. Higher energy intermediate typically has the higher transition state energy. This is the type of reaction we'll look at. Two different carbocations. Carbocations. This one would be more stable. And thus it would be lower. If these are the two, you would put this one lower. That's not always the case, though, what we just described there. In this example down here, the common intermediate. From there, you can get two different products. We'll actually talk about this later in the course. It's the 1,4 product, 1,2 product. 1,4 is lower in energy, but doesn't have the lower transition state energy. Actually, it has the higher transition state energy. That's an exception. What we showed above is more than norm. This is an exception. But we will see that again. Okay? What's below here? Sort of like at the beginning, there's no intermediate here. You see an intermediate? Assuming that this is the end of the reaction. No intermediate. What did we say in here? That's an example of an SN2. If you look at this and this, you'll see that later. Question down here is sort of, how can you make this reaction faster? A very general answer to that.
Lower activation energy.
Yeah. If we can lower that down there, somehow that would make the reaction faster. What could do that? What could lower that activation? Catalyst. What else could do it? No, I don't think heat would lower that. Heat would just allow you to achieve topping capacity.
Add more reaction.
No, add more reactant is not going to change activation. There are a variety of things could do it. Maybe one solvent would make a lower activation energy where another solvent would not. There are numerous things that could do that. Catalyst is sort of a beginning answer. Okay, so those are reaction coordinate diagrams and associated questions that might come with them. Being able to just understand them. In lab, you'll be asked to draw them for your reactions. Okay, let's go back to the beginning. Can we answer such questions now? Two different reactions at the top. Which one of these gives off the most heat? Could you do that? What would you need to do to answer this?
Find
That's just a delta H calculation. Okay? Which reaction is endothermic? Well, that comes from number one. Looking at your answer for number one and just saying which one's endothermic. The one that's endothermic would have a positive delta H. That'll be the one that's endothermic. You calculate delta H is here. We'll look and see which one's positive. Which will be fastest?
activation.
We just kind of talked about some stuff. Are the reactions driven by entropy or not? You did examples of that, right? Okay, see how you do on those? I'll supply an answer key to that. Any questions on this handout? Okay, handouts today. Take a short 2-minute break. Okay, guys. The pink handout is some warm-up questions. On the flip side, we have a schematic summarizing our alkene reactions. Okay? With this being that our alkene, it is a ring. Doesn't have to be a ring. At the alkene. We will cover these sort of sequentially. And then here's our outline. Okay? We will begin with A. The white handout is sort of the more miscellaneous notes. Okay, guys, we're ready to begin alkene reactions. All right? Alkene reactions are going to require even more dedication, practice. Okay, especially here at the beginning. You got to get off to a good start, really dig into it, ask good questions, good reading. All right? I present the stuff, try to do it in a way that is broadly applicable. Everything I do, even the first thing we do, is meant to help you 2 or 3 days from now. Okay, it's a complete package. You can't just memorize isolated bits. You can't memorize reactions. Okay? Analogous to math. Whenever you learn multiplication, maybe in 7th grade, you learned all 5 times 5 is 25. Okay, all this. But did you memorize 128 times 34? No. Can you do that? Yes, because you know how to do math. All right? We need to learn how to do alkene reactions so we can do anything. I try to teach you the fundamentals, okay, the explanations, to empower you to do the chemistry. But it takes a little work on your part. Okay? Again, we build. We build, but we'll also practice, practice, practice. We will repeat common things. It will seem like a lot. But I could give you 1,000 different math problems like I just gave you. Could you do all 1,000 of them? Yes, no problem, okay? Let's look for consistencies. Here's the outline. My outlines, if I'm not already mentioned, very informative, hopefully. What are we doing first? Electrophilic addition. What is electrophilic addition? I would understand what that means. Terminology is important. Involving what type of intermediate? There you go. Well, guess what? That should involve a carbocation intermediate because it's under A, A2. All right? All right, these are the outlines. First reaction is what? Addition of HX to give alkyl halides. That reaction is also known as what?
Hydrohalogenation.
Hydrohalogenation. Yes. And Roman numeral 1 is right here. Okay? It may not say Roman numeral 1 right here, but everything is in that order. All right, let's look at this reaction. We have an alkene. Alkene reacts with HBr. We saw some of this reactions in the previous handout. We can get this product here. What is it? It's an alkyl bromide. Alkene. It's now just an alkane, alkyl bromide. All right? This is an addition reaction because HBr just added to that. You can see that from formula. Take this formula and add HBr, you now have this formula. This is an addition reaction. You know, there's only about 5 or 6 types of reactions in chemistry. Addition, elimination, substitution, where in gene chemistry you call it a replacement reaction.
Yeah, combustion.
Okay, this is an addition reaction. What is the mechanism for this? There's other terminology we can see here. For example, the bromine ended up bonding to what carbon? The tertiary carbon. What other terminology would you use? So we use our terminology to, okay? Mechanism for this reaction. Using arrows. Okay. The pi electrons are a source of reactivity. Pi electrons are not held tight. That pi bond is not a strong bond. Okay? Those electrons can react almost like a lone pair. Not quite as reactive as a lone pair. All right? There is no lone pair here. If there was a lone pair, we could take the proton and electrons move on to bromine, right? It's an acid-base reaction. Here, though, the two electrons in the pi bond go and react with the H. We need to look at both of these. First off, over here, you can either keep this ion covalent or you can go ahead and just make it ionic. Usually I'll just make it ionic like this, but you can also do it covalently. It depends on how this exists. Now, the convention here, what is typically, we do sort of these, like a gate swinging, these electrons. Here's the pi bond, okay? These electrons go and break away, no longer bonded here. They go and they bond to the H, all right? And so we pull them away from here and we go bond to the H. There's my arrow. Well, the electrons have to leave the H because it can't bond but to one thing. So these electrons move on to bromine. Well, that's okay because bromine wanted the electrons anyway. Why would these electrons attack the H? Well, it's partial plus. And these electrons are negative. So they move and attack the H and these move here. What would that give? Well, this here. Because the electrons used to be pi bonded. They broke away and they went and bonded to the H. That carbon over there no longer has the bond. This carbon is now bonded to the H. And there's that bond we just made. Often I will highlight bonds we made with a little zig there. That's a sigma bond now. Single bond. See, these electrons used to be sitting here. They went and bonded to the H. But this carbon no longer has a bond. Pi bond. It's missing a bond, so that's a positive charge. We call it a carbocation. And it is an intermediate here. Now I could have did the same thing down here. I could have showed it ionic and just went and attacked the H. Okay? Now, I thought about trying to do this way. I don't know if this is confusing or not, but look at this. You take your alkene and just do a resonance structure. That is, just take these electrons and move them here. What would that give? That's just a resonance structure where we're just moving the pi electrons around in this structure. What would now be over here? A lone pair. Just take these electrons and move them back over to this carbon as a lone pair. Well, that's now a minus and this is a plus. Okay? Just a resonance structure. Now, if you took these electrons and acted as this is the base and bonded to the H and kicked off the bromine, what would that give? That would give this here. But now this is bonded to the H. But how I did it originally is these electrons, instead of just moving on to carbon as if there, I'm just showing them in most books, this is the way most books all do. The electrons are just moving to going to bond to the H all in one step. At least on the board. All in one movement on the board, okay? Alright, we'll do this over and over and over. You can digest it, you can ask questions, okay? This is our intermediate. Now, at this point, the Br minus, which was formed here, then just basically acts as a Lewis base, and these electrons go make bond to the cation, electrons and cation, and this bond made here, and there's your product. Okay? A two-step reaction. Comments over there. H plus is the electrophile. What's the definition of electrophile? Something that likes electrons. Well, it reacted with electrons. Okay, it must have liked them. Otherwise, it wouldn't have wanted to react with them. The H plus here. H plus is in quotations. It can either actually, well, it's never actually H plus, which is free. I mean, if it's ionic, that means there's probably some water around. But, you know, we say H plus. HBr is a source of H plus. Br minus is nucleophile. What is a nucleophile like? Likes the nucleus, but a nucleus is positive. Nucleophiles like positives. Right? They wouldn't bond to the positive. This is terminology. Two-step mechanism for this addition reaction. It involves what type of intermediate? Carbocation. Reaction coordinate diagram. Boom, boom. You got some type of reaction progress. Some type of energy. Starting material. Let's call that A. Let's call this B. And we'll call the product C. Some arbitrary energy level, A. Where do you want to put B compared to this? Higher or lower? Higher. It's a charged ingredient. It's going to be higher energy. It's charged. Let's put B up here. Where would you put C, the product? It's back down to neutral. But how would it compare to A? You can get out your calculator. What do you think? Do you think it'd be higher or lower than A? Why lower?
It's more stable.
Why is it more stable?
The bonds have lower energy.
We went from a pi bond. Pi bond was broken. What was formed?
Six.
Two sigma bonds. Sigma bond to H, sigma bond to bromine. You can get out your calculator, but I guarantee you it's going to be exothermic. It's going to be lower. Okay? You can just, and so C would be like here. Okay? So what's the pathway? Do we just do a straight line here to here? Or do we have a transition state? Transition state, we fall into that B intermediate well. Yeah? Now the next transition state, leading to C. Right? See, that bromine has to react. Here I come. That takes energy. Making the bond. How high does this, how high do you want this to be?
Lowest.
Just a little bit? I could have even made this a little higher to make it more definitive. Which step is the rate determining step? Yes. First step is your rate determining step. Typically forming the high energy intermediate. Same things we said on the other page, yeah? Is this reaction thermodynamically favored? Thermodynamics, I reckon, includes both delta H and delta S. Is it favored by delta H?
Yes.
Yes. Delta S?
No.
No, because you're adding two molecules together. So I think that question is a little bit vague. It's favored by enthalpy, but it's not favored by entropy. Addition reactions are not favored by entropy because you're adding things together. Okay, look at this reaction. Why did we not react the same starting material with HBr and get that product? Why did the bromine not end up out on the primary carbon?
Because the bromine was partially negative and it wouldn't have wanted to bond.
Is it more so the carbon atoms more stable?
Now you're looking at a different mechanism. Yes, the pi electrons will never attack the bromine because the bromine's negative. Where's the new H at? You got to keep track of your H's. Where's the new H at here? New H is here, yeah? There's no H here. So there's your HBr. That would require that the electrons come this way. First step. First step, same mechanism. And that would give what? The H bonded over here. Again, this arrow, you've got to come from the end over here. Pull these electrons away from that carbon, all right? Like this. Pull them away from this. If you came up here and pulled this away from this, you would grab my hand here. You wouldn't grab over here. And you would pull it, and it would go bond, leaving that without something. Grab it over there, pull it, and go bond to this H, leaving this as what? No bond. How many H's on this carbon? 2. Still only 2 there. You've got to keep track of your H's. Since there's only 2 there, what's the charge? Positive, like I showed. Now Br minus, same mechanism. These electrons could make bond there, and that would give that product on the right, correct? Why did the reaction not go that way? Well, if it did, we would get a different intermediate. That's not the same intermediate as we got up there. This is primary. That up there is what? Tertiary. Which is more stable? Tertiary is more stable. Why? Why is this, how do you stabilize a cation? Do you push electrons towards it or pull away?
Push electrons towards it.
No, if you pull away, you're going to make a cation even worse. How do you stabilize a carbocation?
Push electrons towards it.
You got to push electrons towards it. How do you stabilize poor person? Take more money away from them? No, you got to lend them some money. This carbon is electron poor. But this one's got 3 rich friends, right? Because it's got 3 sp3 carbons. What do?
Push electrons towards it.
Yes. How many rich friends does this guy got?
One.
Only 1. It's branched over here. It's not branched there. It's only 1. It's only got 1 rich friend. Which one's more stable? That one over there, right? What's new? Haven't we talked about how you stabilize cations? sp3 and 2, okay? If this was an intermediate, let's call it ABC. Let's call this D. Where would D sit compared to B? Higher, right? Let's put D here. This starting material has 2 different pathways. All right? Which pathway is it going to take? B or D? B. Why would it go that pathway if it could go this pathway? It's not going to do this reaction. It's going to go with the reaction we showed. Why? It's all based on what? The carbocation intermediate stability. This reaction is said to be regioselective. For a term, I bet you it's in the glossary of your textbook. Or on Wikipedia or any other source. Regioselective. It selects for one region. The bromine ends up bonded at this region, or site. You know, we could say site selective. That makes a little bit more sense, maybe. Site selective. That's what regioselective means. Does the bromine end up on the tertiary carbon or the primary carbon in this reaction? Tertiary. It's site selective, and we call that regioselective. All right? If you did this reaction and the bromine ended up kind of equally on both, you'd say that reaction is not site selective. That reaction is not regioselective. But this one is, and most of our reactions will be. The major product here is the one shown. That's the major product, not this guy from the bromine here. Carbocation stability. Tertiary is more stable than secondary, that's more stable than primary, primary is more stable than just a nothing. But other things can affect carbocation stability as well, such as resonance. Effect on reaction coordinate, we showed that. Lower energy intermediate is going to be here, easier to get to, etc. Okay, what type of reaction did we just do? A hydrobromination of an alkene to give an alkyl bromide. We see that it's a regioselective reaction. We see the mechanism, etc. All right, you try one. What's the product of this first reaction at the top? Typically, we do this reaction with HBr and HCl. Here's the question you want to ask. Where do you want to make carbocation? It's going to be on one of the alkene carbons. Does it react like this and leave this one as a carbocation? Or does it react like this and leave the other one as a carbocation? Where do you want to make carbocation? Top or bottom? Top. Alkene, top or bottom? Top. It would be tertiary. All right? Let's just go ahead and call this ionic. Okay? These electrons pull away from the top. Here it is. They pull away from the top and they go react. The bottom carbon is now bonded, leaving the top carbon as a carbocation. Yank it down. I like to draw in the new H usually. There's the new H. Does that mean there's only one on this carbon? No, how many are on this carbon? Not two more.
Two total.
Two total. There's one to begin with. Now we added another. All right. What's here?
Carbocation.
Yes, there's no H there. There's no H up there. We make tertiary carbocation. What's the next step?
The fluorines.
Chloride. Bam. Those electrons make bond. Showing that with our mechanism arrow. Your mechanism arrow, every time you say use an arrow, you should say these electrons. These electrons in the pi bond sort of hinge down and go make bond to H. That's what that arrow means. Next arrow begins with saying what?
Where the electrons go.
These electrons. Next arrow. These electrons go make bond to carbocation. Every arrow should begin with what? these electrons. Arrows show movement of electrons. And when chlorine adds there, what do we get? We get that product. What is that? 1-chloro, 1-methyl cyclohexane? Does that sound right?
Does it matter if you put the chlorine on the top or bottom?
No, it's not carbon. Yep. Can you do the next one? Where do you want to make cation?
Secondary carbon
Which one?
group. Secondary carbon.
Secondary? You would never make it on primary, would you? Not over secondary. As we go along, we'll pretty much say never make primary carbocations. Secondary is okay, tertiary is better. Let's see here. Have I got product yet? Can you name your product? Can you name it? 2-iodopentane. 2-iodopentane? Yeah, Asian? Everybody do mechanism? You should be doing mechanism, that's... Even when it's simple, you still should be doing it because it needs to become... So many times students come by and tell me, yeah, I know the mechanism, and I say, sure, and then when you actually pick up your pencil, sometimes you can't do it. You have to always do it and prove to yourself, because guess what? Tests are written. You got to make sure you convince yourself. Do you expect this to be a regioselective reaction? Or would you expect the iodine to be like almost equally bonded somewhere else? Yeah, it should be regioselective, because if the iodine, see what we're doing here in terms of terminology is it says we're adding HI across the pi bond. An H and an I across the pi bond. But does the I go here and the H here? Yes. What about putting the H here and the I here? No, you would not add it across that way. That way would involve a primary carbocation. You're never going to do that when you can make a secondary carbocation. Okay, I'm not always going to do out full mechanism. Hopefully you're able to see it. Everybody seeing it? You got your secondary carbocation there? How about the next reaction? Where are you going to make cation? Left or right?
Could be either. That one's not regioselective, right?
This example would not be regioselective. To make cation here, it would be secondary. Both would be secondary. Which one's going to be favored? They will be slightly different, but it's not going to have any favorability. Boom, 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 boom. Could actually get the same product above, but we'll probably, no doubt, also get what? Yes. That reaction is not going to be. Now we're speaking in absolute terms here. What does it mean to be regioselective? What if you got 51% of one and 49% of the other? Somebody might call that, hey, it's selected for one or the other by 2%. Yeah, but come on, is that really selective? So again, absolute. When I'm saying it's not regioselective, what's more accurate is, I could ask you this, which reaction will be more regioselective of the two? The second or the third? Yeah, the second is going to be much more regioselective. But again, the third one I would pretty much say not regioselective. Broadly speaking, 50-50 to the bottom.
When you're doing the ones that are not regioselective, you always do the two different options.
Yeah, because it's not regioselective. Why would you show one over the other? That's what we're saying. You have no reason, okay? At least not in this class. Okay, so look at this here. If you wanted to synthesize 2-iodopentane, the 2-iodoisomer, if you wanted to synthesize it, which reaction would you choose? Would you start with this alkene or would you start with this alkene? You would start with that alkene. So that's getting at designing synthesis. Hey, I want you to synthesize 2-iodopentane because if you can make this, you're going to sell it and make a lot of money. Well, which route would you want to do by? I'd want to make it by this route and make more compound and make more money. So I would want to start with this alkene. If you've done nomenclature yet, what's the name of it? 2-pentane. Okay? Synthesis, let's look at that. How would you synthesize this alkyl bromide? Show a synthesis of it. Now, by the way, you only know one reaction so far, reacting an alkene with HX. So that should be the type of reaction you show. When you get over to organic 2, you may know 5 different ways to make that compound. Right now, you only know one way. Show the one way. But you got to choose the right alkene. Because you always want your synthesis to be regioselective. High yielding. Regioselective. We don't want mixtures. And do the other one as well. What you got? Yeah? You want the double bond here, this starting material. Double bond there would not give you a regioselective reaction. How about the one on the right? Somebody got that one? Uh-huh. There's actually 2 different answers for the one on the right. I see the same for
Is that one or two?
That was the same one.
That's the same thing. You say or. That's the same thing.
With the position.
No, it's the same comment.
There's two different ways over here. We can react this alkene with HCl, or we can react what? Or that?
That's the same thing.
That's the same.
No, this is the same thing. These are the same exact compounds. If you name them, same exact name and everything. That's just turned around. So that's not two different ways. That's the same way showed twice. Right? So understand that in terms of structure and nomenclature. That's the same compound. What is a different starting material we could use? And again, my 6-membered rings don't always connect. Is that okay?
The acetyl.
Yes, you could also have a double bond like that. Because if this reacts, where are you going to make cation? Top or bottom? Bottom. Same cation as here. Both of these react to give the same cation. They both give the cation that's needed. Both of these give that. This begs for a question. Which reaction would be faster? Which starting material shown would react faster to give the product? No, there's not more resonance. There's not any resonance.
Because the one on the left is a secondary carbocation, and the one on the right is a tertiary.
No, they both give the same cation. They both give tertiary carbocation.
Isn't the one on the right gonna have another step? Isn't the one on the right gonna have another step?
Another step? No, they both react with H plus to give carbocation. Which would react faster? Reaction coordinate diagram. They both get the same intermediate, which is called C. They both get the same product, D. Do they start at the same place, though?
No.
Which one's lower, A or B? Do they have the same stability, or is one more stable? Alkene stability, how do you judge it? It was yesterday at 10:20, I think. What time? What? 10:35 yesterday. How do you judge alkene stability?
Number of substituents.
Which one has the most carbon substituents? A. A's most stable. A goes here. B goes higher. Correct? Yes? All right? They both form here. Along the way, they become the same thing. Not at the end, but along the way. Somewhere along the way, they become the same. And they end up to C. Yes, look at it, see it. Which one's going to get to C easier, though?
D. Lower activation energy.
B. B will get there easier. Because it's already closer up there. It's higher energy to begin with. If you're climbing a mountain and you're here and your friend is here, which one's going to get to the top first? Whoever's here will get there easier. Here's your starting point. Okay, go. That one gets there easier. B gets there easier. B will react faster. Reaction coordinate diagram is the way to organize your thinking and to get these answers. Yeah? product is favored in the following reaction. You have to think about that a little bit. It does involve resonance. Think about that, and we'll come back to that at some point. Okay, that was Roman numeral 1. Did we cover everything? Did we cover these things? I think we did. Roman numeral 2. Addition of water to an alkene to give what? Alcohol. We also call this a hydration of an alkene. Okay, alkenes do not react with pure water. No reaction. The skin of an apple is covered with lots of alkene molecules. Those alkene molecules protect the apple from the rain. Alkenes don't react with pure water. Water is not electrophilic enough. We have to include an H+ catalyst. If we have water and a catalyst, H+, we can get a reaction, an addition reaction, and we can add water to the alkene. And we can get an alcohol. You look at the formula. The formula now has water added to it. Now, if you combine water and H+, you can write that as H3O+, yeah? So we'll often see it written like that, water and acid together. What are sources of H3O+? Usually you go to the stock room, you can't just say, give me some H+, or give me some H3O+. You can be like, well, what do you want?
Strong acid.
Yes, you can't just say, give me some strong acid. They're going to say, well, what do you want? What are sources or examples of strong aqueous acid? Sulfuric acid, phosphoric acid, or HF. Now, of those, only sulfuric is actually strong. But the others are strong enough for this reaction. I said HF. You would not want to use HCl, though, for this reaction. Why not? We just got through with that. HCl reacts to give alkyl chlorides. You would not want to use HBr, because you'll end up with chlorine or bromine bonded here. We'll see that. But you can use HF, because F will not bond. Okay, mechanism. Very similar to previous mechanism. The alkene acts as a nucleophile. It attacks the H+. You can just show this ionized. Or covalent. But usually I'll just show it ionized, because this is polyatomic. It's hard to work with it covalent. What you don't want to do is just throw an arrow towards the H2SO4. That is not detailed enough. Where do we want to leave cation? Left or right? On the left. Right. On the left. Correct. Why on the left? Tertiary. If we had did the other way and left cation over here, it would have been primary. Bad. Tertiary, better. Now, what can attack the cation? To get this product, water, oxygen needs to attack. These electrons make bond here. The H's are there. We do not lose the H's. The oxygen now bonds. These H's are here. The positive, after it bonds, is a positive, the oxygen is a positive charge. do charge, right? To go neutral, we need to lose one of these hydrogens. All right. Let's look at this. And these electrons need to move here to become the second lone pair. What can take this? All right, we need to talk about this. First off, I've always kind of allowed this, but I think I should not allow this. We should draw this out. Okay? Here's the structure. These electrons, right? Anytime we use an arrow, these electrons take the H. These electrons move on to oxygen. That gives our final product. But what are we reforming here? This is now bonded to H. That's now H2SO4. And that was our original catalyst. See, this is aqueous. So there's H2O here. This is water, and H2SO4 is the H plus catalyst. And you see we reformed it there, so it is indeed a catalyst. Because only if you reform it do we call it a catalyst, right? Note in the first reaction, we also reacted with H plus. Back over here. Was H plus a catalyst over there? No, we did not reform HBr. But here we have a catalyst. How many intermediates in this mechanism? We have a carbocation. And then we have this species, which is an oxygen cation. Two different intermediates. These would have their discrete energy levels on a reaction coordinate diagram. Which is the rate determining step? Typically, always in these reactions, forming the carbocation is your rate determining step. After then, typically you're then coming downhill. This is lower in energy than this. Yes, it's charged, but everything has an octet. And so it's better than this. Carbon doesn't have an octet. Now, some books, some people will also use water here. Instead of using the conjugate base of sulfuric acid, we could use water. If we had used water as a base and these electrons took the H, we would have made that plus what?
H3O plus.
H3O plus. That's actually strictly more correct, because how does sulfuric acid exist in water? H3O plus. It's always appropriate if you want to use water to take the proton. I like to use the conjugate bases because we actually reform H2SO4. We see it being reformed. You can also use water to do it. The reason we don't want to use like HBr is because if we had Br minus here, it would attack here. We want water. See, these acids here, the anions, the conjugate base of those acids will never attack anything in this class. It will never attack a carbocation. So the only thing there that can attack it is water. And that's why you end up with the alcohol product after you lose the proton. But if we had used Br or Cl, those would have attacked, and you would have got the previous reaction outcome. Okay, this reaction here is actually reversible. You can take an alcohol, and you can make an alkene. We'll actually see this type of reaction near the end of the course. It'll be just the opposite. The mechanism will be just the reverse. Okay? I'm mainly just telling you that now so it's in your notes and you could maybe look back at it when we get to that point. Of course, this way is a hydration. This would be called a what?
Dehydration.
Dehydration. You're removing water.
Why will chlorine attack?
F minus? Great question. It's a little bit hard to explain. We just know from observation in the lab that it tends to not. The electron, fluorine's a good parent. It holds those electrons tight. It also participates in hydrogen bonding, where Cl and Br minus don't. So that tells you it does a little bit differently. It's a great question, hard to explain again, but pretty much it doesn't. In the end, F minus tends to be a lousy nucleophile. Cl minus is marginal, but it will react. Fluorine minus, it just gets to where it's not good. There's just sort of a dividing line there. It's not a huge, but it's enough that it causes it to not be good. Okay, predict product. Can you show product for this first reaction? How's that look? Look good? No? What's wrong with it? What's wrong with it? I think it's good, right? Okay. How about the next one? I don't know why you said no.
Oh wait, no, is that right?
Yeah, that's right.
Oh.
Yeah? Everybody good?
Oh, I forgot to erase the page that I put in.
Where are you going to make cation in? Secondary carbon? And then what attacks cation? Water. But then you have to lose a proton in order for the oxygen to go back to neutral. Right? Okay. How about the next one? Ethanol. HF dry. See, HF can be dry. Sulfuric acid never can be dry. It's the use of an alcohol instead of water. Can anybody show a product here? All we're doing is, instead of 124 times 68, we're going over here and saying 124 times 72. Can you do that one? Sure. You know mechanism. The fundamentals are the same. The only difference is what? The oxygen has, instead of having two H's, it's got an H and an F. That's the only difference. But that doesn't affect the outcome, though.
When we're, doing ETO returns the, or ETO returns the, sorry, when the catalyst returns the nitrogen, so we need to draw out the ETOH fully, like we did with the,
Yeah, I would always draw things out fully. A methyl, you wouldn't have to. Ethyl, though, I would. It's too condensed.
Somebody got product? Somebody got product? One step at a time. What's the first step in this reaction?
Make the carbon.
The pi bond attacks what? H plus. That's the only thing we've done so far. That has to be the first step. Attacks H plus. Where do you leave cation? You got that identified? What attacks carbocation?
The oxygen.
F minus?
the oxygen,
No, we said F minus don't attack. So what can attack? The oxygen attacks. But then the oxygen's going to be positive. How do you go neutral?
the F returns itself.
Something takes an H. You don't take an ethyl. You only take H's. And what's that going to leave you with? I'll draw that a little more. How about that? See that right there? Right? We got H plus, F minus. We can just show that ionized. These electrons attack H plus. We get carbocation here. Where's the new H? I like to draw it in. New H here, right? Yep. What attacks that? Ethanol. These electrons. Bam. What is that? We have methyl, and we have oxygen now bonded there. What's on the oxygen? An ethyl and an H. Yes, let's draw this out. How many lone pairs on the oxygen? One. Was the other one bonded? What's the charge on the oxygen? Positive. Okay, what do we need to do now?
Take the H.
What do you want to take the H? What can take the H? How about F minus? It will take H's. Takes the H. These electrons move here. What do we get?
That and HF.
We get that. What do we reform? We reform HF. This is reacting with ethanol. What's the HF? The HF is the catalyst. It's reformed at the end. It supplies the H plus, which initiates the reaction. Alkenes don't react with pure water, skin of the apple. Alkenes also don't react with ethanol. We've got to bring in something that will react with. Gets a reaction going. But that thing that we brought in is reformed, so we call it a catalyst. So here we did not hydrate it. We reacted with an alcohol. When you hydrate, you make an alcohol. When you add an alcohol, what did we make here? Actually, an ether. I mean, you know functional groups, you can tell that's an ether. Well, that was Roman numeral 3. Addition of alcohols to give ethers. That's analogous in all respects to number 2. Right? What was the difference? We just had an ethyl on the oxygen. But because of that, the final product is an ether. Please don't memorize that alkenes react with alcohols to give ethers. You don't need to memorize that. If you ever ask that, you can just do a reaction and say, you know what, it is an ether. Yeah, it's an ether.
be able to get products, and you get products by your mechanism. Everybody good here? Got to think mechanistically. Remember 4. One thing we'll say is carbocations are prone to doing something. They're prone to rearranging. Prone to rearranging. As we finish up here, let me just introduce this here. Look at this reaction. This alkene reacts to an HBr. For now, we may have predicted this be the product. Cation on top or bottom? Bottom. And then Br minus adds the cation. That would give this product. But actually, that's the minor product in this reaction. The major product has the bromine reacted over here. Bromine ends up over here on the carbon with the 2 methyls. How does that happen? It's carbocation rearrangement. All right? And this is where we'll pick up with tomorrow after the test.
Will we get 50 minutes to do the test?
We get what?